In this video, we are going to look at the differences between linear, quadratic, and exponential functions. So let's start with linear. The most basic form of a linear equation is slope-intercept form, which is y equals mx plus b, where m is the slope and b is the y-intercept. The shape of a linear function is a straight line. The rate of change of a linear function is constant for the entire line. So that means your rise over your run is the same for the whole line, or your change in y divided by your change in x is constant or the same for the whole line. Linear equations can have no x-intercept, or they can have one x-intercept. So an x-intercept would be when the line crosses the x-axis. So for y-intercepts, the number of times the line crosses the y-axis could also be 0 or 1. Linear equations have 0 or no vertices. The domain would be all real numbers. You can plug any number you want into a linear equation. So remember, the shorthand way to write all real numbers is the capital R with the two lines. So you can plug any number you want in for x. You can also get any number out for y. So your range would also be all real numbers. So domain is your x's and range is your y's. So you can plug any number into a linear, you can get any number out. Some possible linear equations. You could have a diagonal straight line, something like this. It would have one y-intercept, one x-intercept, and a constant rate of change. You would go up so much and over so much and get back on your line every time. You could have a vertical line, something like this. This would be the line x equals 9, because every point on this line has an x value of 9. 9, 0, 9, 1, 9, 2, 9, 3. This line would have no y-intercept, but it does have one x-intercept. You could have a horizontal line, such as this one, which would be the equation y equals -7, because every point on this line has a y value of -7. So this would be 1, -7, 2, -7, 3, -7, 4, -7. This line has one y-intercept, but no x-intercepts. So that's the basics for a linear function. Quadratic function. The standard form for a quadratic function is y equals ax squared plus bx plus c. So the squaring, or the second power, that's what makes this a quadratic. The shape for a quadratic is a parabola. This is a U-shaped graph. They can open up or they can open down. The rate of change is not constant. So you don't have a constant rise over run. However, the change of the change is constant. So the second rate of change is constant. Change of change is constant. For x-intercepts, a quadratic equation can have two x-intercepts, it can have one x-intercept, or it can have 0 x-intercepts. So it can cross the x-axis twice, it can cross the x-axis once, or it can never touch the x-axis. For number of y-intercepts, quadratics have one y-intercept. Number of vertices, would be 1. So the vertex would be the turning point of your parabola. So if your graph was opening up, the vertex would be at the bottom, would be where your graph switches from going down to up. If your graph opened down, the vertex would be at the very top. It's where your graph would switch from going up to down. The domain, the numbers you could plug in for x, would be all real numbers. And your range, the numbers you could get out for y, this would depend on if your graph opened up or if your graph opened down. So if your graph opens up, the lowest point you're ever going to get would be at your vertex. So you wouldn't be able to get any y values that are smaller than that. So your range would be any y value that would be, I guess let's say your range would be greater than or equal to the y value of the vertex. So you could get that y value and above. If your graph opened down, now your vertex is at the top, so you can get this y value and anything below it. So your range would be less than or equal to the y value of the vertex. So let's look at what some of these would look like on a graph. So you could have a graph, maybe your vertex is sitting at 7, 5, and the graph is a U-shaped graph that opens up. This would be an example of a graph that has no x-intercepts because it's not crossing the x-axis, but eventually this side would cross the y-axis, so it has one y-intercept. You would be able to get any y value that was 5 or larger. So for this, your range would be y is greater than or equal to 5. So you can get 5 and up. You could have a graph, maybe your vertex is at 5, 1, and this one opens down. So this parabola or quadratic would have 2 x-intercepts. This branch would eventually cross the y-axis, so it would have 1 y-intercept. And your range looks like you can get any number 1 and below. You're never going to get a y value of 2 or 3 because the graph doesn't exist there. So your range, y would be less than or equal to 1. And the last option is that you could have 1 x-intercept. So that would mean your vertex is sitting on the x-axis. Well, let's say your graph opens up. So you have 1 x-intercept. This branch would eventually cross the y-axis, so you have 1 y-intercept. And then for your range, it looks like you can't get anything that's below the x-axis, so your range, y is greater than or equal to 0. You can get 0 and larger. And that's the basics for a quadratic. The last type of function we were looking at is an exponential function. So the basic form for an exponential function is y equals a times b to the x power. So exponentials have exponents. A is your y-intercept, and b is your constant ratio. It's the number you repeatedly multiply by. The shape of your graph, it could be going down, or it could be going up, but it has a bow or a curve in it. So it's not a straight line, it's not a U. Your rate of change is not constant. And number of x-intercepts, you will never touch the x-axis, so there are no x-intercepts. However, there will be 1 y-intercept because it will cross the y-axis. There will be no vertices, so 0 for your vertex. Your domain, you could plug any number you wanted in for x. You could put anything in there, get something out. For your range, though, because we're not going to have any x-intercepts, we're never going to be able to get 0 or any negative numbers out for y. So your range, your y values would have to be greater than 0. So you're not allowed to get out 0. You're never going to have a negative. So if you had an exponential that was growing over time, on the left side of the y-axis, it would be very low, hugging the x-axis but never touching it, and then it would grow as x's got bigger. So that would be growth. Something that's getting bigger over time. You could also have a decay exponential function. So it would start on the left side high and end up low on the right side, but it can never touch the x-axis. So maybe it looks something like this. It just hovers right over the x-axis, gets super close to it, but will never touch it. And this would be a decay function. So you've got growth that's going up, you've got decay that comes down, but they both only touch the y-axis once, and they're never going to touch the x-axis. Let's see what some of this would look like as a table. So here's a table for a linear function. We know that linear functions have a constant rate of change. So that means the change in y divided by the change in x is the same for the entire problem. So if we look at this, our x's are going up by 1. So that's the change in x. And the change in y, or f of x, to get from 5 to 7, I add 2. To get from 7 to 9, I add 2. To get from 9 to 11, I add 2. To get from 11 to 13, add 2. So your change in y is always 2, and your change in x is always 1. So your change in y is 2, your change in x is 1. So your change in y divided by your change in x is 2 over 1, which is 2. So your slope would be 2. Every time x goes up by 1, y goes up by 2. So that's your slope. So it's a constant rate of change. Whereas in a quadratic, our change in x looks like they're adding 1 each time. And now let's go look at our change in y. So to get from 3 to 4, I add 1. To get from 4 to 7, I add 3. So right now, we already know that this isn't linear because the change in y divided by the change in x is not constant. So this would be 1 over 1, this was 3 over 1, and those are not equal to each other. To get from 7 to 12, I add 5. And to get from 12 to 19, I would add 7. So the change in y divided by the change in x is not constant in a quadratic. What if I find the change of y? So I do a second change. To get from 1 to 3, I add 2. To get from 3 to 5, I add 2. To get from 5 to 7, add 2. So the second change in y is constant in a quadratic. So how can I distinguish these apart? In a linear, the first change in y is constant. For quadratic, the second change in y is constant. So the change of the change, or the difference of the difference. So the highest exponent in a quadratic is 2, which is why the second change is constant. The highest exponent in a linear is a 1, which is why the first change is considered constant. So let's look at an exponential. Considering the following table that represents an exponential function. So our change in x looks like x is just going up by 1 each time. Plus 1, plus 1, plus 1. Makes us have less to focus on if the x's are just going up by 1. Then we go look at our change in y. So to get from 1 to 3, I add 2. To get from 3 to 9, add 6. To get from 9 to 27, add 18. To get from 27 to 81, you would add 54. To get from 81 to 243, you would add 162. And then if I went and found the change of the change, 2 to 6 is 4, 6 to 18 is 12. And so I'm not getting a constant second change either. So we have to look for a different pattern. So they're not adding. Is there something that's happening to get from 1 to 3 that you can also do to get from 3 to 9, that you can also do to get from 9 to 27, to get from 27 to 81, to get from 81 to 243? So in exponentials, you have a constant ratio, meaning you can multiply by the same number. So you have a constant ratio. You're going to multiply by the same number. To get from one x value to the next. So if you're having trouble figuring out what they're multiplying by, you can always work your way backwards with division. So if I don't know what 81 times something will give me 243, I can figure it out by doing 243 divided by 81. And I punch in a calculator and I get 3. So that means 81 times 3 is 243. And then I can do 81 divided by 27. Punch in a calculator, comes out to be 3. So that means 27 times 3 is 81. And then I can do 27 divided by 9, which is also 3. So that means 9 times 3 is 27. And 9 divided by 3 is 3. So 3 times 3 is 9. 3 divided by 1 is 3. So 1 times 3. So they're multiplying by 3. So to find that constant ratio, you can use division. Take a y value and divide it by the previous y value. So y divided by previous y. And that's how you find your constant ratio.